Hey, how's it going?
Good.
How's your weekend?
It was pretty good.
Okay, I got everything ready here. Can you see this right here?
Yes.
Okay, cool. All right, so you ready to get started? I got your notes up.
Yes.
Yeah, so yeah, it looks like you guys got some more stuff. Is this what you did on Friday, maybe? Thursday, Friday type of thing?
Yeah.
Okay. Yeah, I was looking at this, like the first, what is this? The first 7 questions on Newton's third law, just, okay, equal, everything's the same. Not very hard.
Mhm.
And did he look at everything on these and grade everything? Because I noticed there was like a not very constructive no on one of them. Did he grade all the problems?
Yeah.
Oh, that was a quiz. What did you say?
Oh, I said yes.
Oh, okay. So he did look over everything. Okay.
Yeah.
Okay, so yeah, I don't think we need to really talk about that first one unless you want to. The first page on your emails, Newton's third law, except maybe the last one. Let me see, hockey player. Yeah, so this is kind of what we were talking about before. The force is the same, and I think you understand that because it's always the same. Newton's third law, it's always the same on the opposite object. But then you start talking about, why does this guy go flying and the other guy doesn't, right? And so that larger effect, that last sentence you write on number 8, the smaller player had a larger effect from the collision. And what is that larger effect, right? Do you know? Like how would we talk about it in physics? Yeah.
The larger effect of, wait, which player?
The small player. Like, what is that larger effect? Think about Newton's second law. So if we have Newton's third law, that's what it's saying. But we can think about this F net, right? F net equals MA. And that's what the larger effect is. Because this is the same. And if this is smaller for him, then that means that has to go up if this is going to be the same. Kind of a quantitative thing for these equations. When you have something that's a constant, right? This is constant. And so to keep it a constant, if something happens here, well, it's gotta go up and down. And if this one goes down, then that one has to go up, or opposite, rather. If this one goes up, then that one has to go down. So that's what that larger effect is. It's a larger acceleration. And that's why he's sending the small player sliding across the ice in a heap, just more acceleration or more velocity versus time, because of course, acceleration is that change in velocity divided by the change in time. I think you guys talked about that a little bit.
Yeah, just a little bit.
Yeah, that's probably the only one you need then for that type of thing, where v is velocity and t is time, and then a, of course, is acceleration. But it's the same acceleration that shows up in force, so that can be helpful. Okay, so now on the next sheet, it says Newton's first law, and then how much does 1 pound of feathers weigh? And so the g actually needs to be a different value. And the reason is because, let's write it out here. He must have just barely looked over this or just skipped through, because we actually have to use different units here. We can only use g equals 9.8, meters per second squared, or newtons per kilogram, same thing, same units. But when we have kilograms, that's the key here, kilograms, because these units have to cancel, right? And everything you did is exactly right, except for the numbers, because this is definitely true, right? But let's look at the dimensional analysis. This is mass, okay? Or let's look here, newtons per kilogram, right? Let me do it down here, actually, this is better. This one is newtons per kilogram, fine. But how do we get newtons here? This is always in newtons, right? It's a force, right? So how do we Newtons per kilogram is not newtons, right? But how do we get it into newtons? We have to multiply by kilograms to cancel. So that's
Mhm.
the reason why you have to convert that pounds. Well, that's the harder way. Either convert the pounds to kilograms, or you have to know this value of G is 32.2, I think, and it's pounds per second squared. Sorry, not pounds, feet per second squared, because it's a distance divided by time squared. So you have to use this value, and that goes for all of them on here. How much does the 19-pound cat weigh, right? If it was 19 kilograms, you would be 100% right. Okay, I'm just looking at it again. It looks like you did convert. So you're good. And you understand that, right?
Kind of. If we could just do another one similar to that for like a refresher,
Of
that'd
course.
be great.
So if you look at this, and everything I said here is correct, and but you did do it right because you have this conversion factor. Okay, you want another example? And then, okay. So how much does, you know, Musk rocket, the SpaceX thing, 1 pound, yeah, whatever, I don't know, 5,000 pounds. I think it's more than that, but it doesn't matter. How much does it weigh? And hopefully you understand here that the words are very important, because the rocket, this is the mass. Again, we would go through that, like you, looks like you've been doing a good job of writing what's given down. And then weigh is that key word where, oh, weigh, this is a force, and it must be in newtons, right? So the mass, of course, is 5,000 pounds. Pounds, kilograms, whatever. We are given, or we need weight. We don't know what that thing is. And then, well, we have also a constant, which is a key part here, that it's given, just as you wrote down G equals 9.8 newtons per kilogram on your paper, that's also given, and because it never changes, it's a constant. But then we look at it, okay, so you're doing it a certain way, so I should, okay. So yeah, let's write this down. There's nothing wrong with what you did here. Newtons per kilogram, that's fine, as long as you have that little conversion factor, which you do there, it looks like. So, I mean, I'll try to do exactly what you're doing here. What is, oh, you didn't write that down. Okay, so that's what you did here. So we need to, what you did here when you wrote 1 lb, 1 kilogram, that's literally converting it. As you see, you're converting that to kilograms. 1 divided by 2.2 kilograms. That's what you wrote on your paper. So we have to do the same thing here. So all I have to say is, well, now it's 5,000. I don't care what it is. This whole thing always works, but just plug in whatever your mass is there, right? So then it'll be 5,000 divided by 2.2, whatever, I'll use a calculator, but it's something like 2,300 or something. It looks like you did it all at once. You're also multiplying. Oh, okay, that's why. Okay, so this, hopefully you're with me here, because it looks like you're doing it all at once, which is good in the way you're supposed to do it. It was just confusing because I didn't see the W. So W is the weight, right? But then, of course, it's this whole thing here. Let me make it much clearer. This is still M. That whole thing is my mass, right? And I just converted it to units of kilograms, 5,000 divided by 2.2. And then, of course, we have to multiply it by G. So 9.8. Because, of course, this equation is always true. Well, yeah, it's always true. W equals mg. I have that here. You can see. And then we just can plug it in over here, 9.8, and it'd be newtons per kilogram. So as I was showing you here on this thing here, well, we have to cross the kilograms to get newtons, and that does work. So kilograms divided by kilograms is 1, so I don't care. And then newtons. So is that all? Were you able to follow that? Okay.
Kind of.
Okay. Which parts, where did I lose you? Or what don't you get? Either one.
So I understand when you set it up and you convert the 5,000 pounds to kilograms, and then
Okay, good.
the 9.8 is the Newton conversion.
9.8
And
is the
then,
acceleration due to gravity.
oh, okay. So why do you put that in there?
Because of this equation here. We're trying to solve for W, yes?
Mhm.
And so W is m times g.
Okay.
So m, we converted it to you. It sounds like you got that. So we did deal with m, but g is just that value, the gravitational acceleration.
Oh, okay.
Now, this is, so does that make sense?
Yeah.
Are you sure?
Yeah.
Okay, so this equation actually is Newton's law. It's
Mhm.
always this. It's always the same. Is that? Do you get that part?
Yeah.
Okay, good. Because, and it's just a special case, right? Where the weight, I mean, my m is the same. I don't care. This is the acceleration due to gravity, mg, and then all the thing is w. So w equals mg. Okay, so I got 5,000. I got 22,000, 22.2 thousand for this final value of weight. We could say 22 point, what is that, 2227, so 22.3 kilonewtons, right?
Mhm.
22,000 kilonewtons or 22,000 newtons. So
Yeah.
this part was clear about G and M and how we got W, the weight of this thing.
Mhm.
Okay, cool. Because that's what number 2 and 3 are on this paper. They're the same. And you did it exactly right. You did your conversion. So you have to go to kilograms, and then you multiply by 9.8 newtons divided by 1 kilogram. That's all it's saying is 9.8 newtons per kilogram.
Okay.
And then once you have that, obviously it's just a calculator then.
Okay.
Okay, I'll move on to gravitation, unless you want to do another one or want to talk about it some more.
Can we do just one more, please?
Yeah, sure, of course. So let's say, okay, so I gotta have units, and since you're converting, we'll keep it in pounds. That's the idea there. So now we have a number, pounds. So that's given. Mass equals 3/4 pounds. Hopefully you're okay with that. And they want us to do what? What do they want us to find here?
How much does it weigh?
Got it. And so if we're looking for weight, we know that the governing equation is W, force, equals mass times acceleration. Well, gravitational acceleration in this case, G. So we can write that down. G is always the same. What is it?
6.67 times 10 to the negative 11.
Little g, baby g.
Oh. Um, I don't remember.
9.8. And then it's acceleration. So either meters per second squared, or you've been writing newtons per kilogram. It's the same, right? This is exactly the same units. It's a good exercise to do that, actually, if you don't know that right away, to convert these units here. Good practice. So that's everything we need there. And so we would simply, the key point here is that, well, our mass is in pounds and our G is not in pounds. There's no pounds to be found. So we have to convert it as always. So we can write it down. So weight, again, weight equals mg. What is m? 3/4 pounds. but we have to convert that thing to kilograms. And so how many pounds are in a kilogram? Since we're converting 2
2.2.
kilograms, yeah, since we're converting 2 kilograms, we want that in the numerator, as you did every time, because then, boom, that cancels. You're left with kilograms. And so to be just really clear here, that is our mass. This is the equation always and forever. Mass, and then we want G. And so I think you said you have it on your paper, so I guess you don't have to memorize it, but it's good. Make it faster for you. That's G. And so to simplify a little bit here, it would be 0.75 times 9.8 divided by 2.2. And since we did all this business with the units, we already know we're going to get newtons, which is fine. So 9.8 divided by 2.2 times 3/4 is 3.34. And that's all. I mean, we did our work on the units here, and so we know over here, so we know that the thing better be in newtons.
Okay.
Is it the conversion that's hanging you up, or finding, using the equation? What do you think?
I don't know. After this example, it seems pretty clear.
Okay. So yeah, definitely do, because it looked like you did it. I know you're doing it in class and stuff, but it's not too bad. It's really pretty easy. And then, but you don't want to forget. So make sure, I recommend doing a couple examples after this, on your own to make sure, and just compare it to your notes and what we do here if you want. And you should be okay on it.
Okay.
So next we got the Universal Law of Gravitation. These look like kind of the same. Oh, they're a little different. Pretty much the same examples, maybe a little different numbers. But you seem, well, the work seems okay. And are you okay on this? Because we did go over it. So I don't want to, if you don't need it, you know what I mean? But whatever you want to do.
The universal gravitation example, right?
Yeah, there's 3 of them here. And like I said, it seems like you did okay. But we can do it if you want, of course.
If we could just do one example, please.
Sure. Let me look at these again. So you're given mass, given distance. There's the pounds again. It's good. So number 2, that conversion thing, like all you have to do is for the mass. Number 3, you're given mass. Yeah, that number 3 is probably a bit harder. So that seems like a good one. He's in Newton. Okay, we can do that. It's too complicated. Let me see. I'm just trying to figure this out. Okay, let's do the moon. That's fine. Let's have Wayne Newton on the moon. One kilogram, so 1/2 kilogram, or 0.5 kilograms. Oops. Okay, mass, and then it's given 7.35. Sorry if it's a little sloppy. So you can read it. Okay, determine the radius of the moon. So I'm glad to see you're doing that. I'm not sure if you're just copying down what he's doing, but or you're solving these on your own, but I love to see that you're writing down the given stuff first, because that is in fact what you got to do. So the tennis ball weighs 1 Newton, and we look at it and it says weight. Okay, that's force. That has to be a force. It's in newtons, so it must be a force. So you can write that down as given information. It's on the moon. Great. That's not great, very helpful, but you can, maybe it is, we don't know, and has a mass of 0.5 kilograms. So we also know that M1, we can call that the mass of the tennis ball. We're just calling it M1. It could be M2, doesn't matter. So we're given that. And we're also given the mass of the moon. If the moon has mass 7.35 times 10 to the, and I forgot my units in the problem, but the kilograms for sure, determine the radius of the moon. So then D, not D squared, but D is what? We don't know. We got to figure it out. So then we'd look at this and say, okay, it must be gravitational law, or whatever you're calling it. You're calling it the law of universal gravitation. Yes. So all of these things, well, that's how we know it's universal law of gravitation. That's what we think. And so we want to write that equation down. So big G, M1, M2, D squared. And so we see that we are given, well, figure out what we're given, that one and everything up here, because of course, G is our constant. And you don't have to write down the units, whatever they are. So the hard part is done and the problem is essentially solved. At least all the hard work is done, right? Are you good with that concept?
Yeah.
Okay, cool. And then, as you know, since we're solving for D, it's the same thing every time. You got to solve for D in the denominator. So let's just do it real quick here. If we want to get D by itself, well, let's bring it out of the denominator. And they cancel on the right side because anything divided by itself is 1. And so then we can divide both sides by FG. So then we have this now. And then, of course, to get D by itself again, we have to take the square root to eliminate or cancel that square. So then we get D is big G, M1, M2, D squared. Sorry, not D squared, FG. So then now is just plugging in the numbers. We make sure we do it carefully. You don't want to screw this part up after all this hard work. So then you got M1.5, great, 1/2, and then it was 7.35, something like that. This is big G, M1, M2, and then we had, I think, a Newton. Easy on us. Yeah, everything looks good, and then we can use a calculator here. Did you get? Did you practice a little bit? You found the E button and all that for scientific notation?
Yeah, I did.
Okay, good. So then for this one, I'm going to get right, 6.67 negative 11 times 0.5 times 7.35. So big old number is basically what you have there, 2.45 times 10 to the 12th. You had 3 times 10 to the 12th, which is good. Sign, and then we get something crazy, 1565638 point whatever, but then we can say 1.57 times 10 to the 1, 2, 3, 4, 5, 10 to the 5th. Sorry, I missed a number. So 565638. So 1, 2, 3, 4, 5, 6. That's how you can do your scientific notation. And the units, of course, is what you want. And since we've been using newtons and kilograms and all that, it's just a standard unit for distance, meters.
Okay.
And that one is the tougher one of these 3 on here, and the toughest I've seen, because easiest one is where they give you that number one, right? They give you the mass, they give you M12, and then they give you the distance also. So squared is easy. So you don't even have to do any manipulations. You just pull out your calculator immediately. Excuse me. But it is, make sure everything's in kilograms. And that's why you had to say, on looking at number one here at the bottom of that page, the first one for universal gravitation, 45.93 G equals 0.04593 kilograms, right? Grams to kilograms. And it's really important, or you get the wrong number. Got to make sure everything's in the right units. Is that good for gravitation? Any questions on it, or another example?
I don't think so.
Okay, good. That's a good sign. So yeah, those are probably good ones you want to know for sure. Those three, know them really well. Okay, now I'm looking at the quiz here, and it's basically just a recap of what we've done tonight. An object or body with no net force acting upon it will do one of two things. Okay. With no net force, will not move until a force. That's perfect. It will remain in motion until another force stops it. And then he says how. It just stays in motion. That's how. Newton's first law, I guess, is maybe what he's looking for there. That's what Newton's first law tells us. So, and this was a quiz, so you did this without any help or anything, right? Like on the fly?
Yeah.
Nice. That's really good. I mean, at least this first one, like that's perfect. It sounds like you really understand it, which is great. Because I mean, the answer is stay or remain in motion, but you gave an explanation, so that's awesome. Don't get discouraged by his red pen and how, because you got 110% points. You get extra points for that answer.
Okay.
So yeah, it could don't let him discourage you. Number two, how much does a pound person weigh? How much does that person weigh? And so we did that, and just a quick recap, right? M times G, easy, right? But no, you have to convert, and that's exactly what that middle thing. So this is what I wanted to talk about earlier. I know hopefully you got it, but just to, like, that's your mass, great? Or sorry, no units down there. That's your mass that they give you, 175 pounds. Hooray for me. I could just do M times G. No, that's what this thing is here. You have to convert. That's what we're doing. And that's why that thing is there. And you say, oh, my pounds cancel. Now I'm actually converting to kilograms. And then of course, G over here. So again, in your mind, you think of this whole thing as the mass. That's just a conversion rate. This is the given mass. So that's good. 175 pounds. So make sure that you do not put 175 pounds. It looks like he didn't say anything, but just that's the mass of the guy, right? Or this woman or whomever. The weight is always in newtons. And since pounds and newtons are not the same unit, the weight is never in pounds. Okay.
Okay.
So 3773 is definitely the answer there. Two engine accelerating down running. One of the engine quits. Okay. Nice. Yes, of course, it would probably be half, right? The acceleration would probably be half. That's what I would guess. But yeah, this is perfect because the mass of the aircraft on the engine. Actually, it wouldn't be 1/2 because you're exactly right, because there's still that mass. I guess it depends, but it doesn't matter. You got that's fine. If you're building a race car and you want to have the best possible, so exactly, Newton's second law, force equals mass times acceleration. They want you to have a high acceleration. So how do you do that? Large force, small mass. And hopefully you said that. In building a car, two things are the mass. That's exactly what you said. Great. And the weight of the parts, because that will be, yeah, that's good. You're going above and beyond with these answers. But I make sure this is clear. Oh, sorry, not mg. It can be sometimes, but acceleration. What is acceleration? Well, divide both sides by m. Anything divided by itself is equal to 1. So a times 1, it's just a. F net. So how do we get a large acceleration? Well, think about it. If F is really large, that means this has to go up because of direct proportionality. And then imagine dividing by a small number. That'll mean this will go up also. So large force, small mass. which is exactly what you wrote, of course. And good, yeah, Newton's third law is pretty easy. But this number 6 here is interesting because you really have to think about each and everything that's happening. And that's why the answer is capital no with 3 underlined lines.
Yeah.
Yeah, what a fool. Like, could have said, I mean, that's fine, but then give me a little feedback, Maybe expects you to come and
Yeah.
say, why is this no? All right, so the thing is like that, it's only, let's have a picture. It's only when one force is in contact. That's the key thing here. If you go back to the very first answer, and it was like a kicking a soccer ball, I think. Your foot and soccer ball are in contact. That's why Newton's third law applies. But this one, why your answer doesn't work is because you are not in contact with the water, right? And I think I see where you're going here, but it's like it's a completely different force, right?
Yeah.
And honestly, I tried to find one here, but Newton's third law is always applicable. It always applies. You exert a force on an object, and it's a smaller force back on you. And did he give you the right answer? Did he write it down somewhere for you or tell you?
No.
Yeah, so you should ask him, but I would say that this situation it can never happen. And why? Newton's third law, right? Every force exerted on an object, that it has to be in contact, that little object will exert the same force. I'm kicking a soccer ball poorly. Well, I'll kick it well, but I'll draw it poorly. And there's a force. Cool. But then at this moment, at that moment right there, only at that moment, there's an equal and opposite force minus for the opposite part. So again, I would say that the words matter very carefully. Describe a situation where you exert a force on an object. Great. You do something to something and it exerts a small force back on you. Okay. So never, but see if he's looking for something special, because maybe he's a tricky guy and he's trying to trick you, but
Yeah.
But also it's kind of important. Do you understand why your example is not like it doesn't work?
I don't really understand why, but I know it's not. I know that it doesn't work.
So they have to be in contact. Imagine you're dropping a coin. You're standing here and you drop your coin in a pond. You said, okay, so here's my coin, but you are not touching the coin anymore, right? So Newton's third law is literally only contact, only ever. I mean, unless you're doing magnetism and electricity, but we're not here, right? It's literally just mechanical forces and you're not touching this coin anymore. So you can't even consider that part there, because the key word is here, you exert a force on an object. Okay, maybe you have a coin, but it's no longer exerting a force on you. That water is exerting the force on you, right?
Oh, okay. Yeah.
And it has to be you on coin and then coin on you. It can't do something else and then you say, oh, the coin did it. Well, no, it was the water that did it that time. So yeah, that one, you seem to understand Newton's third law fine, but that extra little piece there is that it's only when they're in contact. And so hopefully that closes it for you, brings it all home. Okay, so the next page then is gravity and distance. If you're good with moving on, I guess we just went over that quiz, so that's okay. So yeah, gravities and distance. This would be that extra equation, maybe not. Let's see. 82 kilogram man moved to different locations. So his weight will probably change, but his mass never changes, we know. Okay, yeah. So you did have it right there, and you just maybe forgot that D is actually just R plus H. Like in this thing here, FG, we kind of talked about this before. There's your standard equation. You know that one pretty well by now, I would imagine. But then you come in here and you see this one and you say to yourself, or maybe you do, I'm not sure if you do, but these are different equations. Is that what you say? Do you I'm kind of giving away. Do you think these are different equations?
Mm-hmm.
Yeah, the answer is they're not. I've just changed my distance. They're really the same exact equation. And if you use that thing right there, where my distance is no longer just from the center of the earth to the surface of the earth, now I've just went a little bit farther away. I've just added something to my distance. That's what this is saying here. And so let me, if it's not clear, here's my Earth's surface, and then my normal equation, center of the earth, there's D. There's that D. Yeah.
Mm-hmm.
But now let's say, okay, now I'm in orbit as you've been doing. Well, how much is that distance? If this distance is H, well, let's just call this R. I don't care what it's called. It doesn't matter. So now the total thing is R plus H. That's where that R plus H comes from. Because Newton's the gravitational law says it's from the center of two objects. So if you're here, sure, you can call it D because it's from the center of the object to you. So that's D, fine. But it's the same equation. I'm still squaring it. It still depends on the masses.
Mm-hmm.
So even if I go this extra little bit here, this height above the earth, H, I mean, just call the whole thing D. I guess that's what I'm trying to get at here. So that thing now, that's your new D, your new distance, where it's just R plus H, where
Oh,
that's
okay.
R and that's H.
Okay.
Because let me see. Yeah, there's nothing on there. It didn't look like you finished it, but that was exactly right how you did everything here, except for R. It's not in orbit. Oh, okay, okay. So yeah, the altitude there was just the D. So I don't want to go too far without asking you, like, how do you feel about what I said here and your problem on the first one on the page, gravity and distance? Because that's what I was kind of talking about here.
I think that it makes sense, but I'm kind of confused on the question.
Mm-hmm. So yeah, they want you to fill out the table. And so
Okay.
yeah, okay, so yeah, so location, since I don't have the picture, mass. So what they want from you is to fill out this table. That's what the question, to complete the data table below. That's the key phrase there. Use the gravitation to complete the data table below. You'll see that a lot on SAT. I don't know if you're taking it, but most people do, and it seems like you might. So complete the table below. That's your indicator of like your action, what to do. And so we look at, they give you 3 different locations, obviously, and the key here is I don't care where it is. It could be anywhere, but the point is that sea level is 0 meters, right? Prescott is now, and we're talking about from the surface of the earth. And so altitude, yeah, it's a little confusing. That's the total location. What would you say the total location is for this one if you're at sea level and using universal gravitation?
The total location?
The total distance that you would need. That's, I think your value might be a little off. It's the radius of the earth.
Okay.
Does that make sense?
Oh, okay. Yeah.
Okay, good. Yeah. And so that's the location, but it's 1610 plus the radius of the earth, right?
Mm-hmm.
Okay, good. And this one is not whatever that is plus the radius of the earth because it's already giving you altitude. Okay, no, you do have to actually add the radius of the earth because it's altitude is always above the surface of the earth. Yeah, it makes sense. Okay. Does that make sense to you? Or
Kind of.
you have to add that radius of the earth to every single location.
Oh, okay.
Yeah, sorry if I was jumping around and unclear. Is that clear now?
Yeah.
Okay, good. So 1610 plus Well, the radius of the Earth, because you're using gravitation. And again, go back to this picture, it's always based on the center of the Earth. That's why you have to add that radius in. Okay, so that's the location. It may not seem helpful because they already gave us that information, but now you're actually interpreting it and saying, no, this is what it really means. That's my radius. That's the distance that I'm using in the equation. So that's why it's helpful. Okay, now what would you do if you're going to fill out the mass portion of this table? They already give you one of them. So what would these entries be?
Solving for the second weight.
Yeah, you're overthinking it right now. When does mass change?
It doesn't change.
That's the answer. 82 down the column. Make sense?
Mm-hmm.
Okay, yeah. So mass never changes. So if they ask you what your mass is on Pluto, and they give you the mass, you weigh 50 on, or sorry, you're 50 kilograms on Earth, well, you're 50 on Pluto. I don't care where you are. It's always 50. And then weight is when you do solve for this thing. Yeah, weight is in Newton. So you have your force. The governing equation is, well, the universal law, but not just d squared. I mean, you can do d squared. Again, it's the same as r plus h, but now you have this number here. So then if you did it, let's make sure we get it. We should get 803.6 if we plug this in. Our units here, right, for this part of the table. Okay, well, g times the mass of the person, 82, fine, and then the mass of the Earth, I think, is 5.24. That's the mass of the sun. Whatever the mass of the Earth is, doesn't really matter. Well, I guess we want to get the right number. Do you have your paper? I can look it up in Google real quick. I think it's 10 to the 24 or something like that. And then distance of the Earth. I feel like I may have gone too fast. You tell me and we can go over it again.
I'm keeping up so far.
Okay, cool. So 5.97. And again, I've just plugged in the values. Sounds like you're okay with that. Just normal. And then you do that. Well, we don't have to. You can do it as a check, but we're going to get 803.6 because that's what we're solving for. Imagine if we put in d equals 0, because if we go to your notes on the quiz, if we go back, we say, oh, Daytona Beach, the distance is 0. No, right? Because you're not at the center of the Earth. The distance is only 0 when you're at the center of the Earth or the center of the sun or whatever you're doing. And a good indicator was, well, I'm dividing by 0. Well, hopefully you're familiar with, well, you can't divide by 0. And so, yeah, there's a couple key things here. Basically, the mass is the same no matter where you are. And then the location or the value of your distance is not 1610 for the second one. It's 1610 plus the radius of the Earth. So I don't have anything else to say about that. Is that all okay? You good on all that?
Yeah.
Okay, cool. Okay, so now I'm on the next page, universal gravitation, and it is, I mean, you're given two masses, a man and a woman, given in kilograms, straightforward, distance apart. Boom, plug in the values. You don't have to convert anything, and you put it in your calculator.
Okay.
And the next two are similar. Okay, do you want me to talk about number 2 and 3 on universal gravitation, or go on to Newton's first law? What would be more helpful for you?
Newton's first law, please.
Okay, sure. So yeah, I was actually looked at this one before. The mass and weight, this is great. That's perfect answer. And just remember, mass is never changing. It's in kilograms. It is anywhere in the universe, your mass is the same, but your weight depends on where you are. And as you said, mass is the amount of matter within you, and then the weight is the force pulling down due to a planet or a moon or whatever you're talking about. So that's good. Mass and weight. And think of Newton's second law too there. W equals mg is just a special form of Newton's second law. Heavy box on Earth or the moon. So gravity of the moon is different. The weight changes. Perfect. And the moon has less gravity, right? And you said that. That's perfect. The box would weigh less. That's exactly right. But the mass is the same. I think you said that. But it's good to remember. If you travel to another planet, so larger planet typically means larger mass. Yes, much stronger gravitational pull. That little g is not 9.8 anymore, right? It's whatever it is. Just like it's 1/6 on the moon. Divide 9.8 times 6. That's your gravitational acceleration, little g on the moon. Same idea for the big guy. That is much larger. It's the same question. Oh, your weight. Of course, like we've just been talking about, your weight. So the weight does change for sure. So it would change because of what you said. Just take away that word not and everything is correct. Would change because weight is the force of gravity on your mass. Maybe you actually, maybe you put that word not in there on accident on number 4. Is that okay?
Yeah.
Okay, cool. And then pounds, again, go through that as much as you need to, but it looks like you got down. I mean, been doing it in class, but hopefully you can do that on your own with the examples that we went through. But it's the same every time. They give you pounds, that conversion factor, 1 kilogram divided by 2.2 pounds, you're literally converting your mass from pounds into kilograms. And that's the same thing. And then, so just the last problem, or the last one you have, 115 divided by 1, that's your normal mass. This is the conversion factor. And we are calculating mass, and we are using this equation, weight equals m times g. This is m. And then g, of course, okay, whatever, 9.8 newtons, you can say 1 per 1 kilogram. But then you have your thing here, 1/3. Why? Because the planet has 1/3 of Earth's gravity. Like I just said, it's 1/6 on the moon. So if you want it to be on the moon instead of a different planet, well, it's just 1/6, or whatever factor you have. And then, of course, this is all just calculator stuff. G, and this is that extra. Actually, this whole thing is G there, if that makes it clear. That whole thing is G, but that's a conversion, another conversion factor, basically. Okay. So yeah, that is pretty much all the time we've got. Do you have any last minute questions or anything?
I don't think so. I think I'm good.
Okay. Is it still on Wednesday? Your exam? It's not a quiz, it's an exam, right?
I don't know when it is because he keeps
changed again.
changing it, so I don't know.
Yeah. Well, honestly, it sounds like if you do understand everything that we've been talking about, it sounds like you're going to be pretty good for whenever it is. Hopefully before winter break, because you might forget some of the stuff.
Yeah.
All right. Thanks, Julia. Appreciate it.
Thank you.
Yeah. Have a good night. Bye.
Bye.